Well, here we've got a sulfate polyatomic ion. The sulfate's a pretty common ion. You'll find it in sulfuric acid, sodium sulfate. It's one that you really should end up knowing. And I've drawn a Lewis dot structure here for it. You can figure this one out relatively easily because we've got sulfur with a valence number of electrons being 6, and of course 4 oxygens, which are 6 also. So we'll have a total number of 30 valence electrons and a polyatomic ion charge of 2. That gives us a total of 32 valence electrons, and you can count them here. I mean, 2, 4, 6, 8, and then we've got an extra 6, another 6, another 6, another 6. Now, if you've been adding, that comes up with all 32 valence electrons. If you were told to do the Lewis dot structure of the sulfate polyatomic ion, this would be an acceptable one. In fact, this is the one that Gilbert Newton Lewis, back in 1916, of Lewis dot diagrams, came up with. You'd think that would be okay, but there's a little problem, and that problem is that typically the sulfur-oxygen bond is 158 picometers, but in this polyatomic ion, and this can be measured experimentally, they find that the bond length is a little bit less than that, 146 picometers. So it was speculated that there's got to be some double bonding in here that is bringing these oxygens a little bit closer to the sulfur than you'd expect with these single bonds. And this is where we get to our formal charges. The thing with the formal charges is that we might find that there could be justification for a double bond. Would be a typical AP question saying, here's some structures, use formal charges to find out which one would be the one that could account for a double bond or more in sulfur. If you look at all of these structures, they all have our prerequisite 32 valence electrons. Everybody's got an octet, but we've tossed in double bonds, and which one of these is going to be the more likely version? Well, I've come up with our little method of figuring out our formal charges, which is to draw little circles. So I'm going to draw some circles around our oxygen, this oxygen, this oxygen. We don't let this character out. Finally, this. So let me draw circles around all of these. Fast forward. Okay, done. We've drawn our little circles, and these circles represent the control of electrons that each one of these atoms ends up having. And let's look at our oxygen here, and our oxygen has controlled around it 1, 2, 3, 4. Remember, we only use one electron in the shared pair of electrons. So 1, 2, 3, 4, 5, 6. It has control of 6 electrons. And that's what oxygen is supposed to do. So it's perfect. We would end up giving it a formal charge then of 0, which is sort of ideal. But we know we're going to have to add up to a -2. I didn't put the brackets around these because they sort of get in the way. So I've got my oxygen taken care of. And this oxygen here has 1, 2, 3, 4, 5, 6, 7. Well, it's supposed to have 6. So this oxygen has an extra electron, and we'll give it a -1. As its formal charge. We'll have the same thing here because this oxygen is identical. We've got a formal charge of another -1 that gives us our -2. But, whoa, wait a second. This oxygen is going to have a -1 also. And we know the formal charges have to add up to our final charge. So let's see what this sulfur is all about. This sulfur has 1, 2, 3, 4, 5 electrons under control. It's missing a electron. So our sulfur gets a formal charge of +1, which we'll put in right here. And with formal charges, we can see -1, -1, -1, -3, and a +1 gives us our -2. So we did our formal charges correctly, but this is not a nice formal charge arrangement. We've got charges all over the place. So I wouldn't consider this one to be good. Let me put in the rest of the formal charges and we can discuss them as soon as I get them in. So I'll fast forward. Okay, here we've fast forwarded. I've put in all the charges. There was nothing new. We've pretty much made the same counts and concepts that we had before. We now look at our structure 1 and said, nah, not too many charges on this. Structure 2 is interesting here. We've got sulfur. I've changed the sulfur formal charge to green. And you can see I have 1, 2, 3, 4, 5, 6. It's got a formal charge of 0. Okay. Now, this is not bad. We've got only 2 charges, and the substances with the negative charges are oxygen, which has got a high electronegativity. So this is a pretty good candidate. Well, let's look at structure 3 here, where we've got 3 double bonds. We still have a total of a -2. Oxygen has -1. These oxygens have 0. And the sulfur has picked up the -1 charge. The sulfur has controlled an extra electron. Now, this is a bit unlikely because sulfur isn't as electronegative as oxygen is. And if anybody is going to take electrons, it'd be this other oxygen. This makes our structure 2 our more likely candidate. If the question was, which one of these structures has the most likely in terms of formal charges, this definitely would be our candidate because it has the negative charges, which we should have a -2 on the substance with the higher electronegativities. So that meets our requirement. This is going to be our likely structure. We've got a steric number of 4. We've got 4 zones of electrons around our sulfur. So we'd expect a tetrahedral ion with about 109 degrees, which is excellent. And also, we have a shorter bond than we normally have because we have a double bond here, and that double bond is going to be resonating everywhere. I mean, if you lock this sulfur in place and try and figure out all the possible places where you could put this double bond, you'll find them all over the place, and that double bond would end up creating a shorter bond. So this looks really good. In fact, this is the answer that's expected for an AP exam, and it's one that you'll find in most textbooks, where sulfur has 2 double bonds that resonate, and we end up having the nicest set of formal charges, and we explain our -2 charge. However, there's been a change made to this recently, and what it is that there's another model that can be used to figure out molecular structures. It's called a molecular orbital modeling. You'll find it in some textbooks, and it's covered very slightly because it's pretty complicated, and doing the calculations for it isn't as simple as this, where you just draw some circles. It requires some pretty strong computing. Your university, if that has large computing, will use molecular orbital modeling to predict substances. They use structures like this, where we have bonding and anti-bonding orbitals, and they sort of imagine these electrons throughout the entire molecule. And again, the complications are pretty strong, but with sufficient computing, you can get a very sophisticated model of a molecule. And when they've done this with the sulfate polyatomic ion, they came up with a very surprising result. And that was the original 1916 model done by Gilbert Newton Lewis himself. By the way, Gilbert Newton Lewis was homeschooled and went directly to college from that and became one of the great American chemists. And that is that this simple model is the correct one, the one that's got the world's worst formal charges. And the basis of that, they believe, is that oxygen is so electronegative that we have something that is almost an ionic bond. We've got sulfur with really a charge of +2 because of these highly electronegative oxygen atoms. So this is the new correct answer, but you're not going to find that in any textbooks for a while yet because it's so much easier to figure out things with formal charges and the shapes are about the same. So that's our little twist. And that twist is the answer in all the books is wrong. So sulfate doesn't really have any double bonds.